Pluto, a far-off and befuddling body, was once thought to be a solitary and certified planet, a singular piece of our planetary family. Anyway, later upsetting verbalizations by driving astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astounding disclosure. They propose that this cool world is on a potential impact course with Neptune. Yet, how is it that this could work out? Furthermore, what may be the results of such a giant event? Are we seeing an entrancing influenced eccentricity, or is there something else to this oncoming boundless occurrence? Go along with us as we investigate the potential results of a Pluto-Neptune influence. Pluto, a previous planet that was consigned to a more unassuming status, remains a subject of interest and study in the vast local area. As per constant figures by driving specialists, Pluto's circle is perilously near Neptune's. Driving astrophysicists Neil deGrasse Tyson and Michio Kaku are raising the caution about a possibly dangerous fiasco between these two planets, which could represent a huge danger to Earth. Yet, how is such an event indeed even conceivable? Pluto's circle around the Sun is strange compared to some other planet in our close-by planetary framework. It requires a bewildering 248 years to complete a solitary circle, which really means that since its discovery in 1930, it hasn't indeed even completed one round trip. Anyway, the interest doesn't stop there. Pluto's circle is portrayed by its exceptionally unpredictable shape, totally different from the almost round circles of the significant planets. What makes Pluto's circle much more momentous is its tendency of 17 degrees to the ecliptic plane. The way Pluto follows is considerably more whimsical compared to different planets. This tendency and abnormality add layers of intricacy to its orbital example. Maybe one of the most enamoring parts of Pluto's circle is its communication with Neptune's circle. For no less than 20 years in each circle, Pluto really draws nearer to the Sun than Neptune, as opposed to what we would anticipate from their situations in the planetary framework. This prompts the clear inquiry: why hasn't Pluto collided with Neptune? The response lies in the gravitational impacts of other planets. The assessment of Pluto's circle started not long after its discovery. At first, space specialists attempted to make sense of its strange way. Not at all like different planets whose circles lie somewhat near the ecliptic plane, Pluto's circle stood apart with its risky tendency and sporadic shape. The secret surrounding Pluto's circle can be made sense of by the three-body issue in heavenly mechanics. This is tied in with understanding how three objects in space, like Pluto, Neptune, and the Sun, move and cooperate with each other through their gravitational powers. It's like attempting to foresee where they will go in light of where they start and how they pull on each other. For Pluto's case, this issue demonstrates how its circle, Neptune's circle, and the Sun's gravity all cooperate in a complicated manner. Terms like asymptotic libration, scope libration, and the VZK wobbling are essential for this riddle. As per astrophysicists, what's keeping all planets in their circles is a sort of libration. On account of Pluto, what's more, Neptune, this term truly intends that whenever Pluto crosses Neptune's circle, its position is generally no less than 90 degrees away from Neptune. This spatial division is critical in keeping their circles from influencing each other. Degree libration, on the other hand, alludes to the vertical movement of a heavenly body in its circle. For Pluto, this proposes that when it comes nearest to Neptune or some other giant planet, it is situated far above their orbital plane, adding an extra layer of security from potential crashes. One more basic component in this present circumstance is the VZK wobbling, named after three researchers, VZ and K, who concentrated on how objects move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on one another with their gravity. This pulling influences how they move. For Pluto's situation, the VZK wobbling assists us with understanding the reason why its way close to the Sun is so surprising in spite of the obvious irregularity. This effect helps keep Pluto's circle stable for an extraordinarily extensive stretch of time. The VZK wobbling shows that, in spite of the fact that things in space could appear to be turbulent and conflicting, specific examples and powers assist with keeping principal control. These variables assist with safeguarding Pluto's circle, guaranteeing it doesn't collide with Neptune or go off-kilter. This three-body issue influences how we figure out these circles, especially in how space objects pull on each other. Zeroing in on this helps us concentrate on Pluto, our adjoining planetary framework, and far-off stars and planets. Numerical recreations in the late 1980s uncovered that, in spite of these unsurprising properties, Pluto's circle is still wild, with little variations in introductory circumstances leading to massive contrasts over lengthy time frames. Anyway, these peculiar qualities of Pluto's circle have been found to maintain consistency over very extended lengths of time. Later, PC models have helped us comprehend how the monster planets like Neptune, Jupiter, and Saturn impact Pluto's circle around the Sun. Neptune has an exceptional relationship with Pluto, where, for each 2 circles Pluto finishes around the Sun, Neptune finishes 3. This reverberation helps keep Pluto's circle stable. Anyway, Neptune isn't the only factor. Jupiter's gravity likewise plays a critical job in protecting Pluto's circle, and Saturn also helps in that expansive locale. These tests show that Jupiter's gravity alone is sufficient to guarantee Pluto stays on a consistent course for seemingly forever, potentially, indeed, even billions of years. Maybe Neptune, Jupiter, and Saturn are cooperating to guarantee Pluto can continue circling securely in space without running into inconvenience. These abnormalities are significant in the bigger setting of the universe for keeping up with the security and consistency of heavenly bodies. Without these variables, our closed-by planetary framework, as far as we might be concerned, would be a place of far more prominent strife and shakiness. Bodies like Pluto could without a doubt crash into others or be catapulted from their stable circles, setting off a flowing impact on other divine bodies. For Pluto, particularly, with conversations about it possibly colliding with Neptune in what's to come, understanding its circle is critical. This gives us a more clear picture of the dynamic nature of adjoining planetary frameworks. The instance of Pluto shows how, even in the most evidently shaky circles, equilibrium can be accomplished through the complex cooperation of gravitational powers and orbital mechanics. It moreover highlights the significance of consistent perception and investigation of these peculiarities to more readily get a handle on our spot in the universe. Investigating the profundities of space frequently drives us to defy the flighty nature of divine bodies. What's more, Pluto's circle is an ideal model of this flightiness. The possibility of orbital reverberation, which infers the fragile reliance of a heavenly body's circle on its underlying circumstances, is plainly shown. For Pluto's situation, this implies that even slight changes in the Bantam planet's situation or speed can altogether adjust its drawn-out circle. Utilizing virtual experiences has been essential for examination to grasp how Pluto moves in space. These models use complex science to recreate how Pluto, alongside other space objects like Neptune, pull on each other. By modifying little subtleties in the recreations, cosmologists can perceive how even minor changes can have a gigantic effect on where Pluto winds up. In the last part of the 1980s, these reenactments uncovered something very interesting about Pluto's circle. Regardless of having frameworks like asymptotic libration and expansion libration to settle it, its circle can in any case be ridiculously sporadic. If you start with even a slight distinction in where Pluto is or how quick it's moving over numerous years, its way could wind up looking totally different. Regardless of this confusion, Pluto's circle stays stable for billions of years. This proposes that Pluto's excursion around the Sun has a specific order to it, despite the fact that it appears violent right away, particularly when it includes unpredictable circles like Pluto's. This presents colossal difficulties. The intrinsic nature of these frameworks proposes that long-term forecasts are frequently loaded up with vulnerabilities. While mathematical reenactments are a fundamental tool for understanding and predicting what's to come, the behavior of heavenly bodies, they also highlight the limitations of our gauges. These models depend heavily on the precision of starting circumstances and the intricacy of the interactions they recreate. Any slight error or deviation can dramatically change the outcomes, making exact forecasts an overwhelming task. Also, the violent nature of huge circles like Pluto's serves as a sign of the ever-changing and dynamic nature of the universe. While we've made significant steps in understanding space, Pluto's model helps us to remember how our comprehension of the universe is still limited. Understanding the gravitational impacts of the giant planets on Pluto's orbit offers important insights into the broader dynamics of the nearby solar system. It shows how the presence and position of each planet can have sweeping effects on the stability and direction of other bodies within the system. So why are distinct astrophysicists suddenly raising concerns about a potential impact between Pluto and Neptune? In spite of all these complex forces attempting to prevent such an event, Neil deGrasse Tyson, a renowned astrophysicist, offers a book-length perspective on the mysteries of our nearby solar system, especially the captivating example of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides keen analysis on the evolving nature of celestial mechanics and the public's interest in the overlooked corners of space. His position on Pluto's renaming is framed in the ever-expanding knowledge of our solar system. He sees the renaming not as a diminishment, but rather as a vital change according to our developing understanding of the numerous bodies surrounding our Sun. Tyson's approach to celestial mechanics is one of constant learning and change. He sees the complexity of Pluto's orbit as well as its interactions with Neptune from a perspective that acknowledges the unpredictability of space. He suggests that while Pluto's orbit is stable for the time being, it could undergo significant changes in the future. This possibility serves as a reminder of how much we still need to learn about the forces shaping our solar system. In the grand scheme of things, Pluto's orbit is an intriguing case study in the complex interaction of gravitational forces within our nearby planetary system. While its orbit is stable right now, the mysterious elements between Pluto, Neptune, and the other planets suggest that even the most seemingly stable orbits could change over time. As astrophysicists like Neil deGrasse Tyson continue to explore the mysteries of the universe, they help us better grasp the delicate balance that governs the movements of heavenly bodies. The potential for a Pluto-Neptune crash is not necessarily inevitable, but it serves as a reminder of the constantly evolving and confounding nature of the universe. Regardless of the established theories surrounding Pluto's orbit, it's essential to consider the broader implications of these forces for how we understand the nearby solar system and the universe at large. While Pluto's journey is one of fascination, it is also a reminder that the universe is filled with mysteries and complexities waiting to be explored. The concept of orbital resonance, particularly between Pluto and Neptune, is a central part of the riddle. This resonance, where the ratio of Pluto and Neptune's orbits is 2 to 3, is a key aspect of celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance ensures that despite their orbits crossing, the 2 planets never impact each other. This is a result of the gravitational interactions that stabilize their paths, working together to prevent any catastrophic collisions. The importance of resonance in maintaining stability cannot be overstated. It provides a stunning example of how systems in space, even those that initially appear turbulent, can self-regulate through subtle gravitational forces. Understanding this resonance also explains why Pluto, despite its erratic orbit, has remained stable for billions of years. This dynamic is a crucial component of the larger structure of the nearby solar system. The effects of planets like Jupiter, Saturn, and even Uranus are essential in maintaining stability in the orbits of smaller bodies like Pluto. Jupiter, with its enormous gravitational influence, acts as a kind of guardian for the interplanetary system, affecting the orbits of various asteroids and dwarf planets, including Pluto. In fact, some researchers speculate that Jupiter's gravity may have prevented Pluto from being ejected from the solar system entirely. Without Jupiter's protective influence, Pluto's orbit might have been disrupted even further, potentially sending it out of the Sun's gravitational reach. While the idea of a Pluto-Neptune crash might seem alarming, it's important to understand that the concept is rooted in hypothetical scenarios rather than inevitable danger. Pluto and Neptune's orbits are extraordinarily complex, governed by delicate resonances and gravitational forces that ensure their paths do not intersect in a catastrophic manner. Despite the unpredictable shape and inclination of Pluto's orbit, the gravitational dance with Neptune and other giant planets keeps both on stable courses. However, astrophysicists like Neil deGrasse Tyson suggest that even the most stable orbits may experience disturbances over incredibly long timescales. This has raised concerns that small variations in Pluto's orbit could lead to significant changes in its future trajectory, possibly bringing it closer to Neptune. However, it's important to remember that such predictions rely on long-term modeling and simulations, which are still subject to uncertainties due to the chaotic nature of orbital mechanics. The role of Jupiter in stabilizing Pluto's orbit cannot be overstated. Jupiter's immense mass and gravitational pull have a significant impact on the entire solar system, especially on smaller bodies like Pluto. It acts as a sort of cosmic safeguard, helping to prevent potential disruptions caused by other celestial bodies or minor variations in Pluto's orbit. Some scientists hypothesize that without Jupiter's influence, Pluto's orbit could have been even more unstable, increasing the likelihood of a collision or, at the very least, ejection from the solar system. This highlights the interconnected nature of the solar system, where the gravitational forces of one planet can profoundly affect the behavior of others, even those as distant as Pluto. In addition to Neptune's gravitational effects on Pluto, despite being seemingly harmless due to the orbital resonance, they remain a topic of interest for researchers. As Pluto completes 2 orbits around the Sun for every 3 orbits completed by Neptune, their relationship is finely tuned. The 2 planets' orbits are locked in a stable rhythm, preventing any direct interaction. However, even slight movements in the majority of nearby celestial bodies, or the overall configuration of the solar system, could disrupt this equilibrium. While current models suggest Pluto's orbit will remain stable for billions of years, the erratic nature of space implies that new